Buenas tardes. Buenas tardes a todos.
Buenas tardes, profe, ¿cómo está?
¿Qué tal? ¿Cómo estamos?
Buenas tardes, profe.
Asustados por el precio del barril de petróleo.
¿Anda por dónde? Por los $10.
Menos y por mucho. De hecho, reportaron que en Nueva York ahorita el barril puede estar llegando a 1 centavo.
¿En serio?
Literalmente fue en la página de Ecoavisa. Reportaron que el precio del barril de petróleo en Ecuador ya creo que está por $1, una cosa así. O sea,
¡Qué
se fue al
barbaridad!
diablo, se fue al diablo la economía del país.
Bueno, afortunadamente Ecuador produce algo más que petróleo, pero sí eran una buena parte de los ingresos, ¿no?
Sí, siendo honestos, nuestro país, o sea, es demasiado dependiente del petróleo y si es que el precio va bien, estamos bien, y si es que el precio va mal, pues es lo que hay.
Bueno, pero digamos eso, lo que tenemos es que averiguar cómo salir de este rollo para que el arranque de la economía mundial recupere los precios. Pues yo creo que eso es cuestión, o sea, no podemos vivir en esta situación por mucho tiempo, ¿no? Ya lo
Sí,
están,
fue el lío de una reunión que hubo a inicios de marzo en la OPEP.
correcto.
Rusia y Arabia Saudita estuvieron compitiendo a ver quién la tiene más grande, perdón por decirlo así, pero no se me
Sí.
ocurre otra forma de, de expresarle, y que no, que Rusia quería que Arabia Saudí redujera la producción de petróleo porque no hay demanda, porque si no el precio se iba a desplomar. Y Arabia Saudí en cambio decía que Rusia tenía que reducir la producción de petróleo. Y
Ah,
luego Rusia dijeron, no, vamos a inundar el mercado con petróleo ruso, y Arabia Saudí, ni tonta, también dijo, vamos a cuadruplicar la producción.
sí,
Y bueno, ahorita nos fregaron a los,
estamos pagando las consecuencias.
exacto,
Sí.
de que se estén comportando como guaguas.
Sí, sí leí esta mañana que incluso los precios del petróleo norteamericano estaban llegando a ser negativos ahorita. Había que pagar
Sí,
para poder salir de él.
está una joya. Pero bueno, ¿qué más se puede hacer ahorita?
Sí,
O sea,
sí.
la única opción sería que entre los países que conforman la OPEP decidieran todos reducir la producción de petróleo para que la oferta sea menor y el precio suba.
Sí,
Sí, por ejemplo, para países como Alemania y Japón sería bueno porque ellos no exportan tanto, más bien compran petróleo,
claro,
pero para nosotros está triste.
sí. No, no, claro, pero primero hay que salir de este lío del coronavirus, si no, sin eso no hay nada. O sea, digamos, nadie te va a comprar petróleo a ningún
Si es que
precio.
está en un hospital, ¿no? Tienes razón.
Exacto.
En parte
Exacto.
sí, pero siendo honestos, hasta
Ajá,
cierto punto es como que, bueno, ya es una enfermedad y cierto, nos tienen cuarentena y todo lo demás.
claro.
Y bueno, el riesgo más grande sería que pasara lo mismo que con la gripe española, que después en el segundo brote el virus mutó y luego, boom, 5% de la población mundial, chao. Y era en
Sí,
1918, o sea, imagínese ahora con aviones, ya
claro.
sería que será un 10-15% de un montón de reducción de la población mundial. Pero, pero sí, siendo honestos, si es que no se sabe manejar bien esto, podríamos estar ante una depresión peor que la de los años 20, una cosa, y coincide, ¿no? De los años 20, el crack de los 20,
Exacto. Claro.
y como
Después de
nosotros
100 años.
también tenemos dólar, o sea, no tenemos moneda propia, utilizamos el dólar,
Sí,
si es que se fuera al diablo el precio del dólar por petrodólares, se va también al diablo eh, bueno, nuestro lindo país.
claro, sí. Sí, señor. No, bueno, digamos, otra vez, yo no creo que haya una estrategia clara de cómo se va a salir de esto, ¿no? Hay algunos países que están levantando las cuarentenas, pero no se sabe para dónde va eso, ¿no? Entonces empieza una reinfección rápida y el virus este parece contagiarse de una manera vertiginosa, o se surge algún remedio mágico, alguna vacuna que se resuelva a corto plazo, ¿no? Yo creo que eso es lo primero. De resto, bueno, cómo rearranca la economía y después entonces van a necesitar petróleo, van a necesitar alimentos,
O sea,
etcétera.
eso sí, después de que se acabe la cuarentena, al menos he escuchado un montón de amigos que lo que quieren hacer es emplutarse como si no hubiera un mañana, como si se fuera a acabar el mundo y, y beber y todo lo demás. Y cierto, todo el mundo después va a salir después
Seguro,
de
y eso
la
va a ser
cuarentena.
un despegue tremendo, ¿no?
Eso sí, eso sería la esperanza.
Claro.
El lío sería si es que logramos aguantar. Usted, profe, ¿cuánto tiempo cree que dura esta vaina de lo del
Bueno,
aislamiento?
todos los días se oyen noticias distintas, ¿no? Pareciera que hay una vacuna en fast track para agosto, algo así, que podría estar ya circulando para agosto. Pero claro, hay muchas incógnitas al respecto de reinfecciones y cuánto dura la inmunización y todo ese tipo de cosas, ¿no? Pero ya son, este, yo creo que hay que aprovechar el tiempo para descubrir cosas sobre el virus para resolver mayor número de problemas posible y lanzarse a la calle un poco a infectarse, a inmunizarse y a tratar de entrar bien cuando pare todo esto, poder engranar bien la economía para recuperarse, ¿no? Porque no sé qué otras medidas van a tomar aquí, van a reducir los salarios todos a la mitad, para empezar, y mucha gente que no depende de salarios del gobierno, que tiene que volver a arrancar sus negocios. De verdad que es un juego de ajedrez serio la parte de cómo rearrancar la economía.
Tienes razón en eso,
Sí,
especialmente bueno, que de por sí ya teníamos un problema de desempleo en personas de rango de edad que puedan trabajar
claro,
y bueno, esto del coronavirus, del SARS-CoV-2 no ayudó en mucho, más bien lo acrecentó y duro y feo.
claro.
Ahorita como medidas, lo más probable es que reduzcan, tienen que de ley, obligadamente tienen que reducir el gasto público
Ujú,
y,
sí,
y ya, pues, o sea, por ejemplo, del caso de servidores públicos, capaz haya despidos, baja de
claro.
subsidios,
Sí, y hay
capaz
instructivos
subsidios de la gasolina, no sé qué
sí,
pueda pasar de eso.
sí. Y bueno, es la hora de pensar en soluciones originales. Como dicen algunos por ahí, no hay que desperdiciar ninguna buena crisis. Así que es la hora de las ideas. De
Quizás
inventar.
ahorita, no sé, si hubiera dinero, invertir en acciones de petroleras, porque de ley fijo, las acciones de
Ah,
empresas petroleras
exacto.
se fue al diablo y
Sí,
cuando vuelva al repunte, de ley se va a subir las acciones.
sí,
Pero no hay plata.
sí, así es. Bueno,
¿Y
tenemos
usted, profe, qué tal está pasando la cuarentena ya todo esto?
bien,
Creo
bien, ¿no?
que
Está tranquilo aquí, güey, como nosotros, eso es algo así que resultó quizás algo, algo negativo para nosotros fue de pasar del régimen presencial al virtual, pero yo creo que más o menos nos vamos adaptando, yo creo que, y eso nos da algo que hacer también, ¿no? De aprovechar el tiempo durante la cuarentena, nos dio automáticamente una vía para explotar la imaginación y la creatividad, y entonces lo estamos haciendo. Hay otras universidades que, por ejemplo, la EPN creo que debía empezar ya y le dijeron que no empezara. Así que yo creo que la tienen más difícil no haciendo nada, no estando en la universidad, no teniendo contacto con sus estudiantes, para precisamente pensar, ¿no? Pensar juntos en soluciones. Este, entonces yo creo que ha sido una ventaja para nosotros. Quizás, bueno, vamos a tener que sacrificar un poco los laboratorios, digamos, la hands-on experience, ¿no? Pero seguramente vamos a tener que terminar el semestre virtual. Aprendimos en el interín a manejar estas herramientas. Este, así que yo creo que deberíamos aprovechar para pensar soluciones, ¿no?
creo que Newton descubrió la de gravitación en una cuarentena igual
En
por...
medio de una peste, correcto, en medio de una peste que tuvo que irse al campo, ¿no? Para evitar la peste en Londres y fíjate. Nosotros hemos estado escribiendo varios artículos también, aprovechando este, para salir de algunas cosas que faltaba por escribir. Nos aceptaron un artículo en un Nature Index, así que estamos muy contentos. Así, bueno, aprovechando, yo creo que es cuestión de aprovechar el tiempo para aprovechar las circunstancias para otras cosas que no estarías haciendo si estuvieras en modo normal, ¿no?
Profe, una preguntita así. A lo mejor usted sabe, o si ya se ha tomado alguna reunión acerca de las horas de vinculación.
Sí,
¿Y en qué ha quedado eso, profe?
sí, la última vez que escuché eso es que la canciller estaba buscando una manera de que se pudieran cumplir con las horas de manera virtual, así como estamos haciendo nosotros. De que, por ejemplo, hubiera una modalidad donde, como nuestras vinculaciones tienen que ver con procesos de investigación que por ejemplo, no sé en concreto, no recuerdo ahorita cuáles son los proyectos que están andando, pero que, por ejemplo, el estudiante que estuviera en vinculación pudiera investigar por su cuenta y venirse con algunas soluciones en esta modalidad de cuarentena y comunicarse con la comunidad o con representantes de la comunidad para compartir las soluciones de manera virtual, de manera de cumplir las horas de esa, pero no le he dado un seguimiento a esa propuesta, ¿no? Voy a anotarlo para preguntarle a Graciela cómo está eso, porque tú sabes, todas esas cosas deben cumplir con un documento que nos hizo llegar el CES como una semana después que empezó la cuarentena. Y entonces jurídico se pasó como un mes tratando de interpretar y emitió finalmente un documento instructivo sobre cómo se podían usar los lineamientos del CES. Y entonces voy a averiguar cómo quedó esto de la vinculación. Es una buena pregunta.
Ya, profe, gracias, porque algunos estudiantes ya estamos en noveno y nos
Ajá,
faltan horas y chuta,
seguro.
estamos aquí pensando en qué
Sí,
hacer.
hay algunos estudiantes que están en décimo y estaban,
Sí,
por ejemplo, Joshua Salazar estaba pensando cumplir sus horas de vinculación, creo que era hasta marzo, imagínate, ocurrió esto y está ahorita tratando de... Joshua también sabe, y yo le voy a preguntar a Joshua también, porque hace poco tuve una discusión con él y me dijo que estaba tratando de implementar un mecanismo para terminar sus horas.
Yo prefiero gracias.
Bien. Well, okay, so let's begin. Okay, so we're starting a new chapter. Okay, we're beginning with electron phonon interactions. Okay, and I'm going to modify a bit what the normal trajectory that I had in this topic, but of mixing one dimension and three-dimensional formulations. So this is going to be a little of a mix of a class. Okay, I'm going to introduce to you some new tools, some new ways of doing second quantization, some tricks, old tricks that maybe I should have, that I'm going to use as additional information, although it is an alternative way to generate, for example, say, second quantized operators. And we're going to introduce finally the electron phonon interaction. Okay. So let me introduce a second way, which is maybe familiar to you, to second quantize. Okay, and now we're going to apply it to bosons instead of fermions. Okay, so you must be all familiar with the harmonic oscillator. Okay, the harmonic oscillator, a very nice reference problem in physics. So we have we can express it like this. Okay, where K is the spring constant, right? So this is literally modeling a spring in quantum mechanics. Okay, so we have a little spring here.
¿Qué hace usted?
Attached to a wall. Okay, so this is the spring constant, and that spring constant can be related to the frequency and the mass of this block here through the relation, the simple relationship m omega squared. Okay, so you may recall from your oscillations course that the frequency can then be written as k over m square root. Okay, so this is all classical mechanics, and this is the usual way we do. So now we first quantize our first quantization, the usual prescription. Okay, it's going to be to send the classical variables to operators. Okay, so P and X, and now operators, and then these operators obey a commutation relation, which is IH. Okay, so this is the first quantization, the usual prescription. Okay, and now we want, instead of using the first quantized form, because this form now takes you, so this would be H over I partial X, for example, for a one-dimensional second quantized form, would take me to a second-order differential equation, and then this second-order differential equation we know how to solve, okay? But if we don't want to, again, we don't want to do any differential equations, we go to the occupation number formalism. So we go to occupation number. Okay. And a way you already saw of how to quantize this, to go to the occupation number formalism, is to concoct a couple of new operators, A and A dagger, okay, which will be written like this. And I'll tell you in a second why I write all these prefactors and all these power laws and everything. Okay, it's going to be X plus IP. Okay, and these are operators here, and this is a new occupation number operator, and that's a annihilation operator. And then for the creation operator, we have the same combination here. Okay, but you're going to have a minus sign. Okay, so I'm doing all this exercise in 1D first, and then we won't really need to go too deep into the 3D formulation. I'll just write down the results in 3D, and then we'll go into 3D formulation of the electron-phonon interaction, okay? Which is much simpler than the general harmonic oscillator problem. Okay, so now why do I write these things? Well, on the one hand, we know that we must satisfy this commutation relation, okay? And given that we have this commutation relation, now we derive, for example, X and P in terms of A and A dagger, okay? So we, for example, add up these two equations, okay? So the P gets canceled, so we have A plus A dagger is equal to a common prefactor here. Okay, and we get 2x, okay? So that we have that x, now the x operator is going to be 2h over m omega square root a plus a dagger, okay? So that's one. If you do the same, now you subtract the two equations, so now you eliminate the x operator, then you will get the same, an analogous expression for P, which will be minus I, and I leave to you to do that exercise, H omega times M over 2. And then this will be A minus A dagger. Okay? So you see how I obtained this. I mean, we can add and subtract operators with these rules, as long as we don't change the orderings of these operators. We do not have to invoke the commutation relation, and this is just addition. We have not incurred in any non-commutating swaps, okay, that we have to do in this process. Okay, so we have X and P, and we can show now that if we just substitute these two in the expression for the commutator, okay, you can just show, yes?
I think that you missed a factor of 1/2 in X.
Yes.
And let's see.
Oh, it's correct. If you have...
no, because I have a square root.
2 is over.
No,
Yeah.
you can put the 2 in 2m omega, and the other two eliminate that.
Yeah,
Okay.
no, the
At the
thing
end,
is,
yes.
no, the thing is that this 2 should have been here. Okay?
Yes, yes.
Okay, good. Okay, thank you for noticing that. Yeah, I had it correct in my notes. Okay, so we have these two combinations. Now we substitute this into the commutator, and let's just work it out so that you're convinced that all these prefactors are correctly chosen. So we have 2m omega square root. Okay, then you have minus I, so you can take out the prefactor of the x, this factor here, you can take the minus I here, and then you can take the other prefactor, which is H omega, okay, over 2. And this is also a 1/2, okay, and this is 1/2. Okay, so that will be everything that gets factored out except for the definition in terms of the operators for x. So this will be a plus a dagger, and this will be a minus a dagger, okay? And then we simplify this, so this this omega gets cancelled. This I'm missing a factor of m here, yes. We have an m, omega m that gets cancelled with this one. This 2 gets picked up, h bar gets picked up, so I get a minus I h over 2. Okay? And then we can just operate here. So we have this linear property of the commutator. So this distributive property, right? So we commute A with A. Okay, that should be 0. So we have the commutator of A minus the commutator of a dagger, which is this one with this one. Then we have plus the commutator of a dagger A, okay, a dagger A, and then these 2 commute. So these are the only 2 terms that are left. Let me write this. A looks like a 9. Okay, and then this goes like h bar over 2, and then this is a dagger. A dagger is the boson commutator. This should be -1 because of this minus. This is the normal order of this commutator, like we showed at the end of the second quantization class. And then this is minus this because this is a commutator, not the anti-commutator. It's another -1 here. And this just gives me a -2 with this minus, gives me an IH. Perfect. Okay, so this obeys the correct commutation relation if the A's obey a regular boson. Okay, so this is going to be 1. Okay, so this is the regular bosonic commutation relation. Okay, so let me put it up here, maybe with a different color. Okay, so this is how we set up the commutation relations for our fermion operators also. Okay, so here we just have a consistency between the first quantized operators and the second quantized operators. Okay, this should obey 1, this should obey IH. So this relationship here is correct. Each one of the operators obeys the commutation relations that it should. And as we can put all the quantum mechanics in terms of the commutation relations, this contains all the physics in the second quantized space. Okay? Any questions? Is it clear?
No, it's
okay.
clear.
Okay, perfect. Okay, so let's see what happens now if I try, we know that the initial Hamiltonian, okay, so let me write it here. So the initial Hamiltonian was, I don't like red, and I haven't used black for some time, so let me use black. So if we have the Hamiltonian is equal to the kinetic energy, this is a single oscillator, okay, 1/2 m omega squared times x squared, okay? So this would be the first quantized Hamiltonian. What does it look like in second quantized form? So there's a particular combination of these creation operators, which gives me a nice form. Okay, so let's see this combination of A dagger A, and let me substitute now from this previous equations here. Okay, so A dagger A, so I multiply this by this. Okay, so this one is first, and this one is second. Okay, so I have m omega over 2h. Okay, IP, okay, times x plus IP. Okay, now we proceed with this product. Okay, so we have x squared. Okay, these are all operators, but don't make me put all the hats on. Okay, you know we're talking about the operators here. So x squared, then we have x times p times ip, okay, minus ipx, and then we have plus 1 p squared, okay. We proceed with this. Now we get we can just combine. We have x squared, and then we just combine this like this. I'm missing something here, no? Oh yes, I'm missing something here. I should have an m omega here. There's a difference between in dimensions between position and momentum. Okay, and we get m omega here, and then m omega here. Okay, so now we combine these, we can factor out the I and the m omega, and we get xp minus.
Maybe must have also an m and omega to the square m in the denominator of p to the square.
And we need, yes, m omega squared. Correct. Okay, so we're following the calculation. Okay, so now we know that this is just a commutation relation, right? So this is just IH. Okay, and so we can write this finally as a m omega over 2h. Okay, and then we have x squared minus, so we have the minus, and we get h over m omega plus p squared over m omega squared. Okay. Okay, so now we can multiply h omega, this combination a dagger, by, we multiply here. Okay, so we multiply the whole thing by h omega, and we will get a m omega squared, okay, over 2, and x squared, the first term. Then we get minus h omega over 2 plus p squared over 2m. Okay? So you see that now we see now the expression for, this is the initial Hamiltonian here. Let me put it here. This is the initial Hamiltonian. Okay, in first quantized form. Okay, this is some form of the new Hamiltonian. So but we have this additive term here. So let's put it on that side. This implies that h omega a dagger a plus 1/2 is equal to the second quantized form, the first quantized form. Okay, so that's why it's worthwhile to do this exercise in one dimension, because you see exactly all the mechanics, the three-dimensional case. It just brings in the problems of vector calculus in, but it doesn't reflect the quantum mechanical problem. So you see that this is the first quantized Hamiltonian. Now this would be the second quantized Hamiltonian for the harmonic oscillator. So that is should be a familiar result. Let me put it here in blue. So let me put it in the page. Okay, so the harmonic oscillator, okay, is the Hamiltonian is H omega A dagger A plus 1/2. And you know from our previous dealings with combinations of operators that this is just a number operator, okay? So this just counts the number of excitations of the harmonic oscillator. So we know that now the energies of the harmonic oscillator are going to be just. Okay, so this is very easy. So they're just going to be the number of excitations times H omega. Sorry, put it in this. H omega times the number of excitations plus 1/2. Okay, if we have many of these, for example, many of these oscillators here, so we can put an index here and sum over, okay, all these, and all these have the same frequency, okay, then you would have the sum here, and now you would have the occupation of each of those oscillators here. Let's suppose we have n oscillators, and we have n oscillators. Okay, so this will be now my second quantized form of a harmonic oscillator, and now a set of n independent oscillators. Okay, is it clear? Okay, and I'm assuming that every oscillator has the same frequency, so this would be a model. This is actually a model of the solid introduced by Einstein. So we have a crystal, for example, like this. We have a set of points. Okay, and this is actually a model that I'm going to use in order to use diagrammatics to introduce a crystal with interactions between oscillators in order to make a regular crystal where we have couplings between sides. So the Einstein model will be, and I'm sure you saw this in solid state 1, would be just attaching a spring and a mass to each side. This is the Einstein model. Okay, and the Einstein model in real life is really describes what we call optical phonons. It's a very good model for optical phonons, but not for acoustic phonons. Okay, so this would be the Einstein model for a solid, just making these. Okay. Okay, n independent oscillators. Okay, so you see how easy we set up this model. We just did the model for a single spring, and then we said all these springs are independent, so we just add up the Hamiltonians for each of the springs, and here we did this. Okay, so this would be the Einstein model for a harmonic solid. okay? Harmonicity comes from the fact that our Hamiltonian is just quadratic in momentum and position, right? If we had further corrections, okay, so corrections, okay, would imply, and they're necessary, as you know, would imply higher powers in X. Okay, higher than 2. So X cubed, X to the 4th, and so on. Okay, imply okay, higher powers in X. Okay, is it clear? Any questions about this? Okay, so we know how to set up this in one dimension. It's very easy. Okay. So let's take advantage of this and try to see how we can do most of the physics. Okay, much of the physics in just a second quantized form. So let's suppose we apply an external electric field. Okay, so this is an example. Okay, so how we would describe this? So you imagine now we have our single oscillator problem, and we just know that by superposition we can solve the n oscillator problem. And now we're going to put we're going to assume that this is a charged, okay, and we apply an electric field. Okay. So what is this going to do? So we know
Pushing the charge, maybe.
Right. So it's going to push on the charge or pull, and so
Then the spring will
stretch. Right. So we know from our classical intuition, okay, is that this block spring will stretch a bit. Okay. So now we will have sort of an X0 stretch here due to the external electric field. Okay? Okay, classical intuition. So let's see how this comes about in second quantization. Okay? And I do this because in order to incorporate the electron-phonon interaction, what we're going to see is that now, instead of having a static lattice behind the gas of electrons, right, we're going to have displacements from the equilibrium positions of the ions, and the electron is going to see its interaction with the lattice modified, okay, by the fact that the lattice is stretching, okay? So let's see what happens here. So the Hamiltonian, we have blue already. Okay, so we have the Hamiltonian now with the electric field applied will be plus, okay, so the regular harmonic oscillator problem. And then we add the effect of the field. So let's put the field like this. There won't be any confusion if I put E here. So we have now it's something, okay, so this will be the energy. So this is force times displacement. So if we displace by an X, right? So this is a force times the displacement. And this will be the work done, okay? Work done by field, by E. Okay? So you agree? So this will be the Hamiltonian we set up in classical mechanics. Everything has a classical counterpart here. There's no spin. So we can just write the classical Hamiltonian, and then, okay, so this will be the classical Hamiltonian, and then we say first quantize. Okay. Okay, so we first quantize, so you're just putting hats all over the place here. So we know what the momentum is going to be in first quantization. Okay, and then we could just turn this. This will be the regular harmonic oscillator differential equation. Okay, which gives us my Hermite polynomials as a solution. Okay, and here we put the hats all over the place. Okay, so this will be my first quantized in the presence of an external electric field. Okay, but here we don't want to do this with a regular differential equation approach, but we want to do this in second quantized approach. So we take heart with the definitions we had before, and we write this Hamiltonian now in second quantized.
Teacher, can you return to the previous board at the 1 minute, please?
Yes.
Yeah, okay, thank you. I only wanted to see something.
Okay, good. Okay, so we have the P, and now we go back to these definitions, right? Remember that we had a relationship between, we have to go all the way back here. Okay, so we had a relationship now, X in terms of the A's and P in terms of the A's, okay? So we know what the first term looks like, the first two terms, because we derived that one, and this is just the harmonic oscillator form, okay? And then we just write the X in terms of the combination we know is correct, which is E times E, okay? Times H over 2m omega, okay? Okay, and then we get the combination A plus A dagger. Okay, so now this will be my full harmonic oscillator in the presence of an external electric field, okay, in second quantized form. So very nice. So what do I do with this? Let me call this all this combination here, I'll call lambda. Okay, so that I don't have to be writing all this combination, and for sure I'm going to make a mistake. Okay, so I call that lambda, and I write this in this way. Let me just do everything step by step. You can just have lambda plus a dagger. Okay, so this will be our Hamiltonian. So one way to solve this, and this is a strategy we're going to use in a little more sophisticated form when we see polarons, is to make up a new operator. Okay, let's make up this operator A, which is going to substitute now this operator, but now in such a combination that we go back to the original harmonic oscillator form. Okay, so let's see. So let's we now concoct. This is a word I use a lot in my papers. I like it. This is I cook up a new operator here. So we call this A lambda over H omega. Okay, and I build the corresponding creation operator. Okay, and I put a dagger, and I think this is correct. So this will be lambda over H omega. Okay, so if I combine now the condition, okay, so is a boson operator. Okay, this is a valid question. So we have to ask this, and we have to do the commutation the commutation rules for we know the commutation rules for small a, we have to do the commutation rules for big A, and we have to prove that this A satisfies, okay? And this I leave to you. Let me, it's a very simple exercise. So prove that this transformation I'm doing here leaves me with this commutation relation, okay? So you just substitute these definitions in here, use the commutation relations of A and A dagger, and you should obtain this. If this is correct, then the A operator describes bosons again, okay? And we should be able to describe a new effective harmonic oscillator, okay? So let's do the combination A dagger, okay, A dagger A, sorry, A dagger A with this combination here, and what we get is, okay, this relationship here. Okay, so this will give me A dagger A plus 2 times lambda over H omega A dagger plus A, okay, plus a constant. Square, okay? Just imagine multiplying this one by this one, so you get this A dagger A, then you get A times this, then you get this times A, okay? Then you get this squared right here, okay? So it's very, very easy to derive, okay? So let's see if this new operator, you see that here we already have this combination here, okay? And here we have this combination here, okay? So if we multiply everything here by H omega, H bar omega, A dagger A, what do we get? We can write it like, so we get H omega A dagger plus 2 times lambda A dagger A plus a lambda squared over H omega. Okay? Okay, so it's looking a little more like this one. Now we have the H omega combination. We don't have the half yet, and we have an extra factor of 2. So finally, we can write the Hamiltonian like this. If we now multiply, subtract by sorry, if you have the 1/2 that's missing, okay, so we have 1/2, okay. Now we would get the half we need, and then we subtract this lambda over m H omega, okay. Then this is exactly equal to the old Hamiltonian. Okay, minus, sorry, plus lambda A dagger A. Okay, you see what I did? I have, so I have H omega A dagger. Now I have this extra factor, so I have to subtract from this lambda squared over H omega. Okay, and then we add. So how do I lose this factor of 2? Second. So H omega. So I think I got a factor of 2 wrong somewhere. I'm not getting a factor of 2.
The second term is without 2, I think.
The second term is what?
Without the 2.
Yeah, no. Yeah, you're right. There's not a factor of 2. Just adding the 2 terms, right? Right. Okay, good. Thank you. Okay, so there's no factor of 2. So just you have to subtract this term here and add the factor of 1/2, which is another constant, and you get the correct expression here. Okay. So perfect. So this is a new way of rewriting the energy. So, but this is the old Hamiltonian. Okay, so the Hamiltonian in terms of these small a's, and this is the same Hamiltonian now written in terms of the big a's. So, and this guy obeys the same commutation relations as this. So we can write the eigenvalues directly. Okay. The eigenvalues of this with the electric field, okay, is going to be just the energies of this, so we know what those energies are, so H omega, and this will be N, okay, plus 1/2. And then this is just a constant term, so the energy is reduced, okay, by this factor here. Okay? So, okay? So that would be the energy. Let me see. Let me see 1 second here. So, this is a plus sign. Yes. Okay. No, this will be minus. Okay, so that will be the energy, and then we want to, for example, we can also calculate the x operator. Remember that we have this displacement operator. It would be the combination from just a prescription I wrote to m omega square root, and then we have that it can also be written in terms of the new operator. Okay, so this will be the new displacement operator will be written in terms of our new prescription here. Just wait a second, I'm thinking about something here. Okay, so if we translate this in terms of the old definition, okay, of the small a operators, then we have to go back to the formula we had here. So a is equal to this plus lambda over h omega. And this will be then small a plus big A, and each of those had lambda over h omega, lambda over h omega times 2. Correct. So what does this mean? This means that now we get this is the old displacement operator, okay, here. And then you get a shift because of the external electric field. Okay? So this will be shift in position due to electric field, due to E. Okay, is this clear?
Yep.
Okay, so we did that, the whole thing, the whole exercise. We added so we had the sort of our H0 Hamiltonian. We added an external perturbation, which is the electric field. Okay, and we could either solve the problem in first quantization, which would be turning this into a differential equation. But we chose not to. We do this now in second quantized form, and this would be now my new Hamiltonian. Okay, in order to diagonalize this, okay, notice that this will be diagonal in this basis because these labels are the same operator. So this is the number operator, and we can write down the energies directly in occupation number representation. Now, if we add this, then this is a kind of a strange operator here because it doesn't correspond to anything we know. I mean, this would, if we apply this to an occupation number, a ket, right? This would destroy a particle and this would create a particle, right? So this would be kind of a very strange, we don't know offhand what the eigenfunction is going to be, right? So what we do is we introduce a new operator. So this is a kind of a transformation here, which is just a shift, okay, to a new operator. So we can write this everything in terms of a diagonal form, okay?
Teacher.
Yes?
How did you know this new form of this new operator?
How did I know?
Yes, the form.
Well, that's $1 million question, right? So when you're dealing with second quantized forms, now everything is a linear operator, okay? And the big trick is that to make up the correct transformation in order to diagonalize, okay? There are systematic ways to do this, and I'll mention them, okay? For example, there's a systematic way to diagonalize an operator expression through what is called the Schrieffer-Wolff transformation. So this is one way. Okay, this is in the context of condensed matter physics. This is exactly equivalent to the Foldy Voigt-Huizen transformation, which is an order by order diagonalization. Order by order diagonalization. Okay, so this would be the sort of the systematic, okay, systematic way of doing it. Okay, this is the condensed matter version, and this is the particle physics version. Exactly the same thing. Okay, systematic way. Okay, I've used a lot in my work. Okay, but what the really good people do is to make them up. Okay, so okay, how do I find this transformation here? How? Let me put it in red. That's a very good question. How do I find it? You make it up. You invent. You put invent. And that's going to be a whole chapter we're going to see here in the course. Okay, there's a much more difficult transformation I'm going to use, but generally you can put these transformations, you can concoct them by doing a similarity, okay, similarity transformation. Okay, so this is the major fun to each guy that makes up the appropriate transformation in order to diagonalize a problem it's already famous. You can put your name to that transformation. Okay, so that means that you have to sandwich, okay, your non-diagonal Hamiltonian between some okay, find okay, so that's why these guys have their names attached to this. This is a more kind of a perturbative type transformation, and the Schrieffer-Wolff is very much the same. Okay, but generally, if you can find the DS, so that when you sandwich your Hamiltonian, you get a diagonal form. Okay, then this is your prize. Okay. So this is how you would do it in general. You find the appropriate S so that you put the non-diagonal Hamiltonian here and you get out the diagonal form. Okay, but this is generally, okay, this depends on people just putting their butt to the seat and okay, let's see if we add, let's see if we multiply, let's see if we, okay, and we're going to see a detailed the detail, how you do this in this transformation in detail for the Polaron problem. Okay, we will do it for the Polaron. Okay, what you always have to check every time you make up a transformation like this is that your new operators obey are bosonic or fermionic. Okay, so you have to make sure that that you satisfy the correct commutation or anti-commutation relation. The Polaron problem is going to be a mixture, right? So we have the electron phonon interaction, right? So we're going to have an operator that mixes boson and a boson operator with a fermion operator, okay? So that's going to be sort of the most sophisticated operator we're going to set up in this course, okay? But generally if you have only two body interactions, right, at most, then this is the most sophisticated type problem you're going to have, okay? Electron-plasmon interactions or plasmon-plasmon interactions are always two body interactions also, okay? Okay, any other question? So this is sort of the mechanics of many of the things we're going to do in the near future. Okay? Okay. So let me go and teach you some other neat things before we go into the electron-phonon interaction. Let me write with blue. Okay, let me just make more comments. Okay, 3D treatment. Okay, so the 3D treatment of the harmonic oscillator with interaction between. Remember that again. Let me draw my Einstein model. Remember that we started with a bunch of harmonic oscillators non-interacting. Okay. Okay, Einstein model. So you see how easy it was for me to set up this problem, and how do how do we go from this problem to this problem? Which is a real problem we have, right? Now, these guys are going to be coupled like this. Einstein oscillators. Okay, so this thing, I hadn't done this before in a previous course, so we're going to do this with diagrammatics, okay? Okay, instead of boring you with the 3D treatment of the harmonic oscillator, which is just, you know, pages and pages of a operator algebra in 3 dimensions, okay? So I think this is a much more, so we make contact with the previous topic and we treat the boson problem in the Green's function approach, okay? So I think this is a much neater way to go. Okay, so before we go into the 3D treatment, okay, just of the electron-phonon interaction, I would like to introduce a couple of comments that that are going to be useful, okay, in this approach. So one operator that we didn't see in the previous section, in the second quantized section, was the density operator, although it's a very primary operator. So this would be the density operator, the operator, the quantum operator that counts or determines the number of particles, fermions or bosons per unit volume. Okay, so in quantum mechanics, you can write this operator like this. So let's do the first quantized form. The first quantized form, it's not an operator at all, sorry. Not an operator. So the first quantized form, this is a complex number, first quantized. Okay, so in first quantization, this is just the wave function. Okay, conjugate. Okay, so if you want the density at a particular point in space, you grab the wave function, you multiply by its conjugate, and you get the density. So this is the quantum mechanical density. Okay, 1 second, let me plug in my computer. Okay, how do we second quantize this? When you second quantize this density, now it becomes an operator. Second quantization. And I should include this a different description from the beginning. We never talked about second quantizing the wave function. Okay, although we implicitly do it when we write the one body and two body operators. Okay, so how do I second quantize this? Well, we turn the wave functions into operators. Okay. So I hope you find this fun, because this is a different way to derive your one and two body expressions. Okay, so how do we write this? Well, we express the wave function in terms of the creation and annihilation operators. This would be example, beta, and this will be now the phi. And we did this actually in the final exercise of the homework one. So we have some basis function in R space, okay? And then this will be the
Dilation and the creation, the operator.
right. So we use the completeness relationship, and now we wrote the second quantized form of the wave function. Okay. So this creates a particle, or destroys a particle at position R. Sorry, this should be the disruption operator. So this creates destroys a particle at position R, and this destroys a particle depending on the basis functions you're using here. Okay, and it will be a superposition of those basis functions. Okay, so now we can write this, expand each of those wave functions here. Okay, we can put alpha and beta, and then we have C alpha dagger C beta. Okay, and then we have phi alpha. Okay, R phi beta. Okay, so this will be the general expression for your density operator in second quantized form. Okay, and we can for example then derive the Fourier transform, okay, of this density would be the integral over space, okay, e to the minus I q dot r of the, okay, this would be the classical expression. We can put it in second quantization in the same way. Okay, and you substitute this form into the expression of the integral. Okay, so just substitute this summation inside here, and then you can just do extract everything that doesn't depend on a position integration. So we get alpha and beta here.
Teacher, what is Q?
Q is a wave vector. So this is the Fourier transform.
Okay.
Okay. So this is the a wave vector, right? And we have the integral V3 of phi alpha of R dagger phi beta. Okay. Okay, so okay, let's suppose we know here some and we're missing here the I Q. Okay. So now if we have the wave functions here, we can do this expression, and we obtain some coefficient for this expansion, and we will have the expression for the density at Q equals to 0. Okay, density as a function of Q. We can obtain for example, the limit in which Q is equal to 0 very easily, right? If this is an orthogonal basis set, then this would be just the summation of alpha and beta. This Q equals to 0 will give me just the orthogonality relation between these basis functions. So this will be delta alpha beta. So this will be C alpha C beta delta alpha beta. So this is the operator for Q equals to 0, would be just the number operator here. Okay. So the nice thing about this this way of doing things is that now you can write what we used to know about about the second quantized forms of any operator. For example, you now grab an operator and you want the second quantized form of this, you can just write the first quantized form, okay? And you use now your second quantized form for the wave function, and you sandwich the operator here, okay? This will be my wave functions in second quantized form, okay? And then you derive our prescription for, okay, for formulating second quantized operator. So this will be sum over L prime, for example, choosing those as labels. We have, just so that you remember this, CL prime, and then you get dr3 by L dagger V by L prime, okay? And this is the matrix element, right? L, V, L prime. And this is our, okay, second quantization prescription. Okay, for one-body operators. Okay, so you see that it's a very nice way to obtain. So you again connect first quantized form. This will be the expectation value of your potential in first quantization. Then you second quantize your wave function, and you obtain the second quantization prescription for your interaction. Okay. Okay, so any questions about this? So this is just something that we will use in the electron-phonon interaction as a much more cheap and something that you might remember much better than just remember the prescriptions that we had before in the first part of the course. Okay?
Okay, Profe.
What else? Yes. Okay. Okay, so I'm going to leave as homework. I decided that it would be good to, instead of trying to remember all the exercises I propose here for the homework, I'm going to leave this as an additional problem. So you add them to the homeworks, and you might compensate for some slips you had in the regular homework, and you can have your complete grade. So solve this, so write this down for generic Q. So what is the form of this operator for generic Q? Okay, problem. Okay. Okay, good. So I think that with those are the notes I wanted to make before telling you about this. Let me just check.
Could you explain in more detail what means a generic Q?
Well, in the last line here, I evaluated for Q equals to 0, right? So I set Q equals to 0 here, and I could use the orthogonality relation. If Q is different from 0, I can no longer use it, right?
Mm-hmm. Cierto.
Okay, and here assume plane waves. Okay, I expect you would assume plane waves, right? But just in case, plane waves.
Okay.
Okay. So that you
A
know
Q
how
different to 0.
So a Q is different from 0. So you know how to do this interval. Okay. Let's see if I was going to say anything else. This. No, okay. Okay, so now let's begin formulating the electron phonon interaction. Okay, so electron phonon interaction. Okay, so as I told you, I did not want to do the bulk exercise of the harmonic oscillator in 3 dimensions, but I want to treat the electron phonon interaction in 3 dimensions. Okay, so this is just the gist, okay, of the heavy exercise of deriving this in 3 dimensions for the harmonic term. We know now what the harmonic term is going to look like. Okay, so it's going to look like a set of oscillators, non-interacting oscillators. But now I want to represent this term, this new term for us. Okay, this is going to be Ij. Again, you write all these things in your classical brain first, and then you have prescriptions to derive this in first and second quantization. Okay, so now we're going to have 2 kinds of coordinates here. Okay, so this is going to be the electron position, and this is going to be the ion position. Okay, as usual, we use the big R's to denote the primitive vectors on the lattice. So I use big R here, and R small is going to be the position of the electron. Okay, so now we imagine the lattice here. Okay, and now we have an electron moving around here. Okay, we know that the ions are going to be positively charged, right? Because electrons were taken away from them when you built the crystal, and they're wandering about. Okay, so now there can be fluctuations in charge depending on the charge density of the electrons. Okay, but so this will be described by R. Okay, and these will be described by big R. Okay. Okay, good. So now this is the electron ion potential. Okay, so this is the electron ion depends on the coordinate of the electron and the coordinate of the ion with which it is interacting. Okay, and you sum over all electron ion pairs. Okay, E ion pairs. Okay.
Teacher, in this case, we consider an infinite lattice.
Yes, yes, this is an infinite lattice. Yeah, yeah. Then we should treat any surface effects separately. Okay, so this is an infinite lattice.
Yeah,
up until now, all our systems.
Pero en todo caso que sea igual.
Sorry.
And one electron goes to pass between the ions.
Yes.
Moving.
So this is the static lattice. So all the R's are fixed.
The ions.
And the electrons are moving for arbitrary R, right? So for any distribution of spatial distribution of electrons, you have the interaction here. Okay. So now let's suppose what you're saying, right? So let's suppose that now these ions are going to move. This one moves this way. This one moves this way. This one moves this way, right? Okay, so
The lattice is moving.
So now the lattice is vibrating, for example, under thermal fluctuations. Okay, so I'll call this displacement U, to use the same notation that we would use to describe the harmonic approximation. Okay, so now we have that the electron ion potential is going to be, evaluated at the position of the electron, okay? And then we have the position, the original position of the ion, and now this ion is going to be displaced by, okay? And it's labeled by the same side. So this side is a J, for example, so it has the original position J, and then displacement around that particular J. Okay. Okay, now we're all set up to do so if this is a small displacement with respect to this difference here, then we have that this is going to be the original interaction or potential between the electron and the ion, okay, plus, okay, an additional term which we will describe it the following way. So this will be minus, I have a minus sign here, we have minus, and then this will be the vectorial displacement of the ion times the gradient. Okay, and this is just a generalized Taylor expansion in vector form, electron ion potential, evaluated at the equilibrium position. Okay, so this is the vector Taylor expansion. Okay, let me write here for reference. How do we get this, the general form of that expansion, okay? So a general form of vector Taylor expansion. Okay, so that you can use it in any context you want. Okay, so if we have a scalar function, which is a function, okay, of some position and some displacement, okay, then you can write your vector Taylor expansion in the following way. So this will be again the unperturbed, okay, so this is a displacement. Okay, this will be the undeformed case, okay, without displacement, and then you have 1/2 of A dot grad F of R, okay, evaluated, okay, F of R, it means that the function, okay, the grad of the function is evaluated at R without any displacement, okay. Then no, this has no coefficient. Okay, then you have 1/2 A grad squared F of R plus 1/3 factorial A dot. Okay, and this has sort of a trivial way of generalizing this expansion here. Okay, so you see that this would be very simple in one dimension. This will be just a derivative. This won't be a vector, so this will be a displacement if it's the same direction of the derivative. Okay, and you would get back the one-dimensional Taylor expansion, and this would be the way to generalize it to many dimensions. So you can see that if you apply this expansion here, you get back your this first two terms here. So what is the electron-phonon interaction? Well, it's simply identifying this second term here. And put it in full, okay? So that will be the electron-phonon interaction. The electron-phonon, okay? The phonon interaction, okay? We'll have the following form. So if you sum over all the lattice sites, okay? This will be now the displacement of each of those sites dotted into the gradient of the electron ion potential, okay? Evaluated at their equilibrium positions. Okay, and this is the V of R dependent on R. Okay, so now with the with our setup that we established before with the Green's functions, we can just introduce, this is the displacement operator, which we know how to second quantize now with the previous tricks I showed you. And then you calculate the gradient of the potential interaction between the electrons and the ions, and you get this term. And now you can calculate this, this operator, for example. This is really the first quantization is just quantizing displacement, okay? And this is just a coefficient, a vector coefficient. And the second quantization, we will use the form that we derived before, because the deformation is made up of bosons, okay? Phonons in this case, and we're going to obtain the second quantized form of this operator here. Okay? So let's stop here, and we continue tomorrow with this setup. Okay. Any questions?
Teacher, the term of the gradient is BEI, electron ion.
Ion, electron ion. Yes.
Okay.
Yes.
Okay. Thank you.
Okay. Okay. I just said something that was not completely right. Remember that this guy is here depending on
the position of the electron.
A position of the electron. So this is going to be a one-body potential. Okay. So this will be in terms now of a one-body second quantized form. So notice that this is going to be in general of this form. So remember that this displacement was some kind of an operator that looked like this. Okay, and this is a one-body operator, so this is going to look like this. Okay, let me put it on. Okay, so this will be the with some coefficient number, some coefficient here, which is going to depend on the matrix element of this potential, right? In order to write this, and this will not necessarily, yes, this will be like this. So this will be some coefficient times this combination of fermions, okay, and bosons. We'll derive the specific form tomorrow. Okay. So notice how now we're mixing types of excitations in this because, okay, on the one hand we involve electrons, on the other hand we involve bosons. Okay.
But in this case, what will be the difference between bosons and fermions for this operator?
Ah, come on. This will be bosons, right? So this will obey the boson commutation relations. Okay, and this will be fermion, so they will obey the anti-commutation.
Yeah.
Okay, so they will have different statistics, okay, associated with each type of particles, and of course this acts only on the space of electrons. This acts only on the space of bosons. Okay, so we'll have a combined boson, okay, wave function, right? So now our bracket will involve both types of excitations. Okay. Okay. So no, this is easier than you think. So we'll now have, for example, in the expansion of this, we'll have interaction lines that connects electrons and bosons, and interaction lines that connects electrons and electrons, and bosons
like
and bosons. Okay.
An electron emitting a photon and then interact with other electrons. Something like that.
That's it. Yeah. So for example, an electron
Porque
collides with an ion, it makes it move, so it emits a phonon, right? In this case.
Yes.
And this phonon interacts with another electron, so you have all kinds of different kinds of interactions. Okay.
Okay.
So you see that this already looks very much like particle physics or quantum electrodynamics or quantum chromodynamics. It's pretty much the same formalism, just brought to the realm of condensed matter physics. Okay.
Vamos
Okay.
a palmar.
Sorry.
Nothing.
Okay. So let's stop here and we'll continue tomorrow.
Thank you, Profe.
Okay.
Profe.
Ajá.
¿Sí me escucha, profe?
Sí, te escucho, sí.
Ay, perdón, es que no sabía si es que mi micrófono estaba bien. Profe, quería preguntarle una cosita. Lo que pasa es que ahorita estaba revisando la clase 12 de sólidos y la clase que usted subió tiene simplemente una duración de 24 segundos.
Ay, sí. Debe ser que cargué la clase que no era. Ok. Ya lo voy a corregir. Ajá.
Gracias, profesor. Nomás.
Chévere, muy bien. Vamos a grabarlo para tener todo aquí. Ajá, dime.
Ya, a ver, chévere. Déjame ver. Déjame le comparto. Ya, justo aquí en esta partecita de aquí, nosotros llegamos ya simplemente a tener esta interacción con este bol aquí. Pero mi pregunta era, si aquí ya no, la interacción ya no depende de los estados K, porque los estados K se simplificaron, ¿por qué la interacción sí, por ejemplo, para sacar la interacción, para calcular la interacción, por qué si pongo que depende de K? ¿Por qué aún siguen dependiendo de K si el estado K?
No, claro que depende de K. Lo que pasa es que digamos, el K va a quedar metido, o sea, va a ser la etiqueta asociada. Recuerda que la interacción representa la integral, ¿ok? El valor de expectación. Y entonces, ya tú asociaste a cada una de esas, de las patas de la interacción, una etiqueta asociada al propagador que estaba pegado ahí, ¿ok? Entonces ese propagador tiene una etiqueta K, entonces esa pata particular de la interacción queda asociada a esa etiqueta. Entonces,
ya queda asociada a pesar de que no se simplificó.
Sí, claro, se simplificó, pero digamos, él queda con la etiqueta para poder parametrizar el valor de expectación. Tienes que recordarte de qué vector, qué propagador iba pegado ahí, ¿ok? Y por eso adquieren esas etiquetas en la interacción, ¿ok?
Ya, ok, profe, esa no va a ser mi preguntita, gracias.
Muy bien, chévere. Muy bien, entonces ahora sí paro la grabación y nos despedimos.